Hello guys, I am Kalidas Tapadar. Welcome to Quality and Welding Metallurgy. Today we are discussing on basic metallurgy of welding. Heat input. The rapid heat input and high energy density involved in welding causes very different thermal effect than do conventional heat treatment. Very rapid heating cycle, fraction of second to few seconds, high peak temperature in excess of the melting temperature and relatively rapid cooling rated to ambient temperature, fraction of second to many minutes are all involved. A typical thermal cycle for an arc welding process schematic is there. The heat input of the given process is most easily defined for electric arc process. It is simply arc voltage times arc current divided by welding speed. Since arc lost some energy to the surrounding space by radiation, convection and conduction through gas and flat shielding media. Less than 100% efficiency of energy transferred to the weld zone occurs. Heat is equal to X into voltage into amperes divided by welding speed, where X is equal to efficiency factor. Typically, efficiency factor is typically between 40% to 95%. However, for most welding procedure, it is difficult to measure X mean efficiency. Reliably, and all normal welding procedures are written without using efficiency factor, like it is assumed to be 100%. In this SI system of unit, the heat input is determined by measuring the welding speed mm divided by second. Then the result is in joules mm or divided by 1000 kJ mm. This is more universally used description of heat input. Typically, value for arc welding range from 0.1 to 10 kJ mm, 2.5 to 250 kJ per inch. Heating rate. The effect of the rapid temperature rise during the initial heat cycle in welding have not been analyzed extensively, but do have some important implication. The most important is that any existing segregation of alloy elements or impurities in the base metal will not be evened out by diffusion because the time available is too short. This can lead to a local region in the base metal right next to the fusion line where the localized melting can occur. This is most likely to where previous segregation in base metal exists, for example at grain boundaries. This region may contain higher than average concentration of alloying elements and or impurities, which cause a lowering of the melting temperature. The regions is therefore called the partially melted zone, PMZ. This localized restricted area of the melting may simply solidify Again, as the temperature fall after welding, or it open up under stress to form a small crack, usually known as liquefaction crack. Peak temperature, the high peak temperature reached in welding near or above the melting temperature of the base metal are for in excess of temperature in conventional heat treating process. There are two major results. Grain size in heat affected zone large and largest next to the fusion line at the weld metal. This increases hardenability in transformable steels and may concentrate impurities which are segregated to grain boundary. This may lead to form a hot cracking. All traces of work hardening and prior heat treatment like temperature age hardening will be removed in at large part of the hedge, and size of the resin effect will be larger as the heat input rise. Cooling rate. The rapid cooling cycle for welding after solidification is complete or caused by the quenching effect with the relatively cool part metal which conduct heat away from the weld zone. However, the cooling rate must be evaluated since important weld zone properties such as strength, toughness and cracking susceptibility are affected. As the cooling rate increase, like as the temperature fall or rapidly, such as ferritic martensitic steel or some titanium alloys, the high temperature phase in the weld metal and particularly in the hedge is quenched. Since the actual cooling rate experience of given point varies with location and time after welding, some characterization is necessary. The most used technique is assessment of welding procedure test, but this is expensive and not particularly useful in predicting the effect of changing variables such as heat input. In the welding of steel, the time spent dropping through a temperature range characteristic of transformation austenite to martensite or other transformation product like benite, ferrite plus carbide is becoming a standard test. The characteristic time is measured in seconds for the given weld metal or hedge. Has reason to drop for 800 to 500 degrees centigrade and is often written as DT 8 to 5. A large number of signifies a slow cooling rate. If weld zone properties are not as desired, it is possible in some cases to improve them by altering the cooling rate in the welding procedure. Two main methods are used. The first is heat input in a given situation slow down the cooling rate. Preheating by warming the base material before welding. Also slow down the cooling rate with higher preheat leading is slower cooling rate. Combining preheating and heat input variation is called procedure control. Further control of cooling rate effect can be included in welding procedure by defining a value for a interpass welding temperature in multipass welding. Effectively, a preheat value for each succeeding passes are ordered to ensure a cooling rate within a grain range. Metallurgical effect of the welding thermal cycle. Weld metal solidification. Solidification of weld of metal take place in unusual manner compression with casting. The molten weld pool is contained within a crucible of solid metal of similar chemical composition. Since the melting temperature of the base metal is reached, the fusion line and adjacent hedge experience very high temperatures for short time. The result is rapid grain growth. This large grain acts as a nucleus and the weld metal solidifies against them and assumes the crystallographic orientation of the atomic structure in the large hedge grain. Only the grain with an orientation given rapid growth into the weld metal produce dendrite, and the result is called epitaxial growth. There is very region of melted base metal in the base metal right next to the fusion line, which although 100% molten is not stirred welding due to viscous effect during mixing. This region is called the molten unmixed zone and is usually very narrow, typically 0.1 mm to 0.004 inch wide. Since diffusion is not enough, time out very difference with the weld metal chemistry and segregation in the base metal will persist in this region. It is also region in which any segregation produced in the weld metal may collect in static region and also persist. Initial growth during solidification into is often planar and cellular growth occur as the growth rate increases. Through columnar growth and dendrites form as a faster growth continued in the bulk of the weld metal. As growth of dendrite proceeds into the molten weld pool, segregation of same of the alloy and residual elements in the weld pool occur as the forming solid reject some of the elements into the liquid due to the lower solubility in the solid state. As a result, the remaining liquid near the end of solidification can contain significant higher level of some elements. This can lead to formation of crack, fissures in the weld metal. One example in the concentration of sulfur, phosphorus, oxide and carbonate grain boundary in many ferrous and nickel alloys, which alone or together with themselves and other elements can form complex eutectic of low melting temperature. Growth of dendrites tend to follow the direction of the heat flow generally perpendicular to the freezing isothermal at a given instant and moving toward the welding heat source. As it traverses the joint line, consequently at slow speed, dendrite curve to follow the advancing solidification found in the elliptical weld pool. At high welding speed, the pool is an elongated teardrop shapes and dendrite tend to grow straight toward the weld center line. Thus, any knot crack formed at high welding speed tend to be right down the center line of the weld, while at slower speed they are between the dendrite. The filler metal used for situation prone to hot cracking often contain elements which will mitigate the cracking problem by combining with the offending element to render to harmful. Manganese is often added to the ferrous alloy to combine with sulfur. Since the chemistry of filler metal often different from the base metal, and since the weld metal contains some melted base metal, the diluted filler metal regions is called the composite zone. All of the regions mentioned here show the single pass weld. Heat affected zone. Several zones are formed within the heat affected zone by the combination of heating rate, peak temperature and cooling rate depending on the alloy system. The subcritical hedge occurs when the peak temperature is below an important temperature for the metal being welded. This could be, example, the crystallization temperature in work hardened metal, the solvus temperature for precipitation hardened alloy, or the allotropic phases change temperature for transformation hardening alloys. Above the critical temperature, the grain size increase, especially in transformation hardening alloys. Two regions exist in this high temperature zone. First one, fine grain heat affected zone. This grain exists when an allotropic phase change decrease the average grain size in comparison with the grain size in the subcritical region. This occurs, for example, in the intercritical temperature regions in steel. Quartz grain heat affected zone. This region occur at the high temperature when all phase change are completed. Grain size tend to increase up to the fusion temperature. Strengthening mechanism. There are three fundamental strengthening mechanisms used in metal and alloy, which can be affected significantly by welding thermal cycle in the heads: cold working, precipitation, edge hardening, and transformation martensite hardening. Are all influenced by heating, melting, and cooling. Aspect of rapid thermal cycle experience in the weld zone. Metal and alloy may have one, two, or three mechanisms of strengthening in the place before welding, and the followers will have to consider the overall effect of the following comments, all which may be applicable in a single weld. Work hardening alloy are annulled during the weld metal cycle, during the weld thermal cycle. Dislocation density is reduced, grains are crystallized and may grow larger depending on the temperature reached. In the non-visual hedge, in the unaffected base metal, the lower peak temperature reached usually affect only physical properties such as electrical conductivity. The visible hedge will have lower strength compared to the base metal. This will occur in virtually all cases, since the grain growth in part of the hedge will lower the strength of even an annulled but fine grain metal. This visible change are schematically shown below. Work hardening. If the heat input is low, two factors may minimize the loss in strength. The annul may be incomplete, leaving his final hedge strength somewhat above the annul value, and the size of the hedge may be small compared to the thickness of the material, providing the annulled region with support from surrounding stronger metal. This increase effective joint strength. Precipitation, edge hardening. Precipitation hardening alloys go through more complicated changes, and edge hardening also used to describe this process, which was first noticed as hardening of aluminum alloys, rivet containing copper for aircraft construction, in which hardness increased as a function of time delay before use after the rivets are manufactured. The most important industrial alloy system is utilized. Precipitation hardening are aluminum, nickel, titanium and copper. The phase diagram of binary alloys suitable for precipitation hardening two important features: a significant solubility of an alloy element in the primary metal, maximum solubility limit of several percent, and the rapid solubility drop from the maximum limit as temperature drop with carbon as a typical composition used alloys. A secondary virtue of the chosen composition is responsible temperature range of the single phase solution at elevated temperature to simplify heat treatment and allow some variation in temperature for solution treatment. Usually the composition of alloy has precipitating element added to less than maximum solubility, but this is not always so. Alloy elements added to levels in excess of the solubility limit will solution strength. The alloy in addition precipitation effect. Single elements may be involved, as may two or more. Copper is an element which precipitation hardens aluminum alloys. Magnesium and silicon together do the same. The solvus line at the chosen composition should be at a reasonably high temperature, so that a range of the precipitation hardening temperature like T1 can be used. The range of the T1 to the quench temperature T2 is important parameter. Precipitation hardening results from the precipitation of the particles of a fine dispersed second phase at low temperature after all precipitates are dissolved by heating to the single phase region and quenching. A tempered treatment called a solution heat treatment. Some reheating to temperature below the single phase temperature is often used to cause diffusion to increase and promote second phase precipitation. This is called a precipitation heat treatment or artificial aging, and the whole heat treatment process is shown schematically here. In some case, the precipitation hardening is not necessary, and the alloy hardened at room temperature over period of time. This is known as natural aging. The progress of changes in hardness, also strength, under isothermal heating as a function of the time is shown below. When an alloy capable of precipitating hardening is welded, the thermal cycle imposes further heat treatment of the weld zone. The thermal cycle of weld is a thermal bump compared to the heat treatment and has variable temperature and time at temperature. The result is complex in terms of the response of the alloy in the weld metal and head. In addition, the alloy can be supplied in two conditions: fully precipitation hardened or solution in annulled precipitation for precipitation hardening after fabrication. Let us consider the effect of the single weld using two welding procedure on both fully hardened and solution treated material. One procedure will be high heat input leading to very slow cooling rate. We will also consider the effect of the post-weld heat treatment PWST, consisting of the conventional precipitation hardening treatment. A full solution treatment after welding is usually not possible due to the probability of distortion in the structure at high temperature, particularly close to the melting temperature. Consider fully precipitation hardening metal first joined to the conventional butt weld configuration. The weld profile shown below use horizontal dotted line to included to the hardness of the heat. Heat treated base metal occurs the zone to be welded. The solid line show the effect of the welding cycle on the hardness across the head. On one side the weld metal and the hedge on the other side. The dashed lines show the resulting hardness after a precipitation hardening heat treatment. The procedure has been low heat input. For remove from the weld center line at the right side of the diagram, the peak temperature reached from the thermal cycle is too low to affect the precipitation in the hardness does not change. As peak temperature rise, a phenomenon takes place called reversion, which does not appear in the conventional discussion of the heat treating. The smallest precipitates have a large surface volume ratio and are relatively unstable compared to the larger particles. When hit with the thermal bump from the weld cycle, the small one disappear locally to form a highly saturated solid solution, thus softening the local region. The larger, more stable the particle being to grow and average, becoming larger and lowering hardness progressively as the peak temperature rise. The graph shows the continuous decrease the hardness once the solution treatment temperature is reached. All precipitates are dissolved and hardness is very low. As the fusion line is approached, grain size increase, lowering hardness metallurgically, but no other changes take place. In the weld metal, assumed it is same chemical composition, solidification produce a solution treated cast metal. When the structure undergo the cooling cycle after welding with low heat input, the material is effectively quenched, thus retaining the solute atom in the solution. Submitting the structure to conventional precipitation heat treatment after welding, no overall solution heat treatment will have the following effect. The previously unaffected base metal will be somewhat overaged, assuming that was the maximum hardness before welding. There are reversion will reharden to approximately maximum level. The overage region will age, further softening it. The solution treated zone in the head will reharden. The solution treated weld metal will reharden if it is of the same chemical composition, autogenous weld or matching filler metal. If it is of the different composition, it will be partially respond or not respond to the precipitation heat treatment, depending on the final weld composition. Weld metal often retain as cast properties in precipitation hardened alloy or partial value of the base metal properties due to dilution effect. Change in the high input precipitation hardened metal has two major effects. The high heat input extend the size of the head, and instead of a solution treatment occurring in the weld metal and head near the fusion line, the alloys is annulled due to the slow cooling rate. This means that the final equilibrium precipitated is present and no response to precipitation heat treatment will occur in those regions. The result is shown below. These two examples show clearly heat using low heat input is or likely to retain the original precipitation treated properties in more the weld zone. If solution heat treatment material is weld, the heat input start the precipitation process. For a low heat input, hardness rise at the peak temperature until the shallowest temperature is achieved. Then the hatch close to the fusion zone and the weld metal are solution treated as before and kept the way by a rapid cooling rate. A post-weld precipitation heat treatment now has somewhat different effect. The unaffected base metal is full hardened, then the following effect occurs. The slightly edged zone overage, lowering hardness. So, the solution treated zone in the hatch and weld metal fully hardened, assuming aging and autogenous weld metal or matching filler metal. If high input is used, the previous comments on extend thermal effect and production of annual zone in the weld metal and near hatch still apply. Then the post-weld precipitation thermal treatment will have the following effect. The unaffected base metal will fully harden, as with the low heat case the edge region will cause overage, but its size will larger. The annulled regions is weld metal hatch will not respond and will stay soft. These four scenarios show that the most effective ways to retain heat treated properties in precipitation hardened alloy is to weld with the low heat input on solution treated material, followed by whichever precipitation heat treatment is appropriate for the application. Transformation hardening. Transformation hardening alloys experienced an allotropic phase change at elevated temperature. Cycling the material through the phase change temperature or temperature range altered the grain size, which is small at the time of new phase appearance, and rapid cooling after the phase change can produce metal stable transformation produced, which are usually harder, stronger and more brittle than the equilibrium product formed on slow cooling. The visual changes in grain size are shown schematically below. The major change from the work hardened alloy is the appearance of two fine grained regions, one for crystallization of the ambient temperature phase and one for the nucleation of high temperature phase. The most common industrial alloy example of transformable alloys are carbon, manganese and some alloy steel which form austenite at high temperature in exceed of about 700 degrees centigrade. On fast cooling, they may transform to martensite or benite rather than the equilibrium product of the ferrite plus carbide. Other metals of industrial importance which experience similar martensitic behavior or some titanium alloy and aluminum bronzes. During welding, a transformable metal is exposed to the every temperature from amine to melting under rapid heating condition, is held at a peak temperature for a short time and is then cooled at rate between fast and exceptionally. This experience is entirely different from conventional heat treatment, which feature slow heating rate. Is isothermal peak temperature held for long and controlled period of the time, controlled cooling rate quench, and possible isothermal follow. And possible isothermal follow-up heat treatment such as trace relief or tempering. Response of weld zone to thermal cycle are therefore more complex. Metallurgical than would be expected from heat treating knowledge. The metallurgical important zone produced in single phase weld in a transformation metal, for example, hardenable alloy steel. The unaffected base metal is defined at temperature below lower critical temperature. Temperature allow which the austenite start to from the A3, which is about 720 degrees centigrade in carbon manganese steel. In alloy, the following equation can be used to estimate transformation temperature in centigrade. Transformation on slow cooling equation is below there. Close inspection on unaffected zone reveals the carbides are somewhat broken up and sulfurized before the lower critical temperature is reached, so that the visible has started at temperature above 50 degree centigrade below the critical temperature. These temperatures are sufficient to cause trace relief tempering and precipitation hardening. Hence, the experience of subcritical has as a metallurgical importing zone, where the temperature is between the temperature where austenite start to form A3 and higher A3, where all ferrite carbide is gone and alloy fine grain austenite remains. For eutectite steel, the temperature range is single temperature, the A3. In the intercritical zone, the austenite form is often close to the eutectite composition, so it is quite hardenable and may form martensite on cooling. The fine grained hedge is just above the upper critical temperature A3 and extend to peak temperature region up to 100 degrees centigrade above it. The final austenite grain size reduce the hardenability in the range, although some carbon gradient from carbide dislocation still exists because of lack of time or for diffusion, especially in bonded microstructure. In the quartz grain hedge, grain growth of the austenite take place right up to the fusion line temperature above 1400 degree 450 degree centigrade. Austenite composition is more homogeneous than it is in the fine grain zone, but gradient still exists. Quartz initial microstructure hot rolled rather than normalized steel slow down carbide dissolution and diffusion. Excavating gradient remove and increase local hardenability. Higher heat input promote diffusion but also cause larger grain. Large austenitic grain size increase hardenability. for given composition, increasing the chance of forming martensite for a given cooling rate. Martensite is hard, strong, brittle and susceptible to hydrogen assist cracking, HAC, also called a cool cracking. This varied microstructure in the hedge involving varying grain size, two homogeneous phase and mixed phase region have complicated response to cooling rate following weld. Most welding cooling rates are relatively fast, inducing a quench in conventional heat treating times. When austenary survive low temperature due to the hardenability, transformation to low temperature product, benite or martensite will occur. In alloy steel, the temperature at which martensite and benite start to form under isothermal condition can be estimated by so and so. In continuous cooling circumstance, this temperature are depressed. Therefore, the coarse grain zone and some of the fine grain intercritical zones may be form brittle martensite or benite, reducing toughness. Tempering with a post-weld heat treatment is necessary to restore toughness in those areas. The multipass weld is transferable alloy. The above effects are complicated by the overlapping of the thermal cycle in a given area, causing reheating and cooling effect on an already varied microstructure. Thank you.